So once you create that particular data structure, that creates a different data structure with different nodes of the employees that you're looking for. And once you're able to figure out what particular employee ID you're able to look for, it has a pointer to the original table that gives you the data you're looking for that particular employee. So in other words, it's a faster way to look up the data that you're looking for.
One of the things that we are trying to do with Friendly is to bring new people to the stage. So I cannot think of a better person to do that with than our next guest, Nabeelah. Give it up for Nabeelah.
Hello, everyone. Hi, I'm Nabeelah Yousuph. I am from Barcelona. Well, originally from Nigeria, but currently live in Barcelona. I'll be speaking about a particular query that we noticed that was lagging a bit within our production systems and how we were able to figure out what was causing the issue and finally the fix. So basically, the 8-second nightmare, how one change reduced latency by 99.9%. So who among you guys have ever been to a food truck festival here? Well, apart from the good weather, I mean, you're there for the good food as well. So imagine you're there, you decide to join a queue, and you give or take the orders that come from said truck should come around 3 to 5 minutes per person. So you join the queue because it isn't that long, and unfortunately, by the time you join the queue, a series of mishaps happen in the kitchen, and then the queue gets longer, people are hungrier and grumbling, and you decide to leave it in search for a better food truck that is serving food faster. I'm going to segue quickly to the domain I work in within my company, which is the time tracking domain. And at the most basic concept, what we basically do in this time tracking domain is we allow employees to be able to register their worked hours and compare them against what their employers expect them to work. So let's say, for example, my employer expects me to work 8 hours per day. I should be able to clock in and out, aggregate everything to 8 hours for that particular day. So unfortunately, well, not really unfortunately, but within the time tracking domain, just last month alone, we had over 70,000 shifts just alone recorded within our database. So you can imagine within the lifetime of our company where we have multiple employees from multiple companies creating shifts, you can imagine how many shifts are recorded within this particular database. It can run into millions of records. But luckily for us, we don't really have to wait for our intuition to be able to figure out when a certain query within our time tracking domain is slowing down or causing users to be unsatisfied. Within our platform team, we have a series of threshold values where queries that are less than 1 second are the best case scenarios, and we try to average within 1 second to 4 seconds. However, whenever a query is going beyond 5 seconds or more, we tag them as slow queries. But whenever they are going beyond 1 minute, we terminate them to avoid dragging the entire system along. So unluckily for us, one of our services within the time tracking domain was slowing down within. And this particular service was actually the top of our logs, of the slow query logs. And these slow query logs, we normally register them within a particular service that we call Datadog, which we like to call a software engineer's best friend. But then we have other plethora of monitoring services and also observation tools that we also check out for these slow queries as well. So within Datadog, one of our staff engineers, Mark Riera, was able to figure out one of our services that was really lagging slowly within this particular record, and it was actually topping, going on the top of this particular logs list, basically. And it was taking 8 seconds long, and if you remember with our threshold values, anything beyond 5 seconds is tagged as a slow query, according to our platform team. The name of this particular service is called the Update Incident Aggregate Shift Location Service. I know it's a mouthful, so that's why it requires a slide of its own. But For us to be able to understand what this particular service does, we need to understand the feature that it works under. And the feature that it works under is called the geofencing feature. I'll try to give like a small analogy of how it works within our domain. But basically, whenever an employer that owns our application enables this geofencing feature, and for example, they decide that this conference room is where I want all my employees to work from, they can choose to be able to log the coordinates of this particular conference room inside the application, and then set a radius of, let's say, 100 meters. And any employee that decides to do any shift action, that is like a clock-in action or a clock-out action, outside of said radius is tagged an incident. So let's say I woke up, I'm lazy, I do not want to come to work, this particular workplace to work. I can create a shift at home. However, that shift is tagged an incident. Another way an incident is also registered is if my employer decides to enable this geofencing feature, and then they forgot to put the coordinates of this particular conference center within the application, any shift, regardless of whether they put a radius or not, is also tagged as an incident, meaning that the workplace location coordinates are missing. So the way it works basically is that we have our shift model here, where we have our clock-in, clock-out, reference dates, and the employee ID, which are created anytime an employee clocks in. And whenever they clock in, and a adjoining shift location is created, which has the shift action, whether it's a clock in or a clock out, the action time, meaning what particular time this particular action was created, the attendant shift ID, which references the shift that we are trying to explain. Out of radius is basically if the employee clocked in or created a shift within that said radius the employers expected them to clock in within, or if the employers forgot to put their coordinates, and this workplace missing information will be true, basically, alongside with the employee ID. So basically, since we already understand a bit about what this particular service does, we need to understand why exactly it was being the top of the slow queries log in our Datadog. So within our service, we have this particular method, and the reason we knew via Datadog was that Datadog gave us a SQL, this SQL in its logs, basically. And in its most basic format, what this particular method does is that it grabs all the shift location, meaning that all the shift locations that I explained here earlier, grabs them by the employee ID. We filter out by the range that we want. Incidences are what I tried to explain earlier, employees that did not clock in within the radius, or if an employer forgot to put the coordinates within the application, and then we grab the employee IDs that we're passing down here. So basically, we're grouping by the employee ID and then returning the count. Simple enough, this is what the method does. And this is the application record with the scopes that are using this particular method. Basic scopes, just keep in mind that the by range is also joining in the attendant shifts, and incidences are basically an OR of both the out of radius incidences and workplace missing information incidences, and the SQL as well. So now that we already know, or Datadog has shown us that this is giving us the slow query, or being slow, how exactly can we investigate deeper on why it is being slow? Well, in our own case, we can either slap an explain or an explain analyze. Technically, they kind of do the same thing, only that the explain won't run the query, while the explain analyze will actually run the query. So if you have anything that can mutate your database records or so, do not run the explain analyze if you do not want that to happen, basically. Okay, so I was saying earlier, we are talking about the explain analyze to investigate deeper if you want to actually run the query. And this is mostly useful if you want to be able to get the cost of the query line by line, basically. So let us run this particular SQL keywords and see what particular outputs it is. Unfortunately, because I cannot really run my production database here, I will just be showing you the outputs we got. So I have a VS Code open, set up with the values. Can everyone see it well? All good? Awesome. So here we put the explain, and what explain does is give us a tabular output of what's going on under the hood within this particular query. I'll just be focusing on the columns within this table that are really necessary for this talk, so I don't really prolong it that much. So here we have the table column where where it's basically showing us the tables that are participating in this query. And if we go to the possible keys, before we can go into what possible keys does, we need to be able to understand what indexes does. So let me quickly go back to my slides. And in a nutshell, basically, what indexes does is just creates a different data structure. So, for example, like the attendance shifts I was talking about earlier, where we have millions of records. And let's say we want to be able to filter out all the shifts for a particular employee. What happens in this particular case is that if we try to do that on the original table, we have to filter through, do an entire full table scan on millions of data records. And you can imagine how mostly inefficient that would be, and how it would take a toll on our resources, basically. So how indexes work is whenever you wrap a particular column that you constantly query within your application, it creates a different data structure where you are able to query that instead of the millions of records table that you have originally. So once you create that particular data structure, that creates a different data structure with different nodes of the employees that you're looking for. And once you're able to figure out what particular employee ID you're able to look for, it has a pointer to the original table that gives you the data you're looking for that particular employee. So in other words, it's a faster way to look up the data that you're looking for. And it has different types. The individual, which I tried to explain earlier, meaning that an index is only wrapping around one particular column, and we have the composite index, which we have an index wrapping around multiple columns. And this comes, well, the composite index comes with its own set of rules. And the one I'll be speaking mostly about here is the order of the columns, how we order the columns within this particular index. So if we go back to the output that we have here, let's go back to the possible keys. And basically, what possible keys in this case is telling us that attendance shift locations, SQL is saying that these are the indexes within the attendance shift locations that I can use for this query, depending on what query I am doing here. But how are we able to figure out what particular indexes are within the attendance shift locations? And one way we can do that is by running this particular keyword, which is show indexes from whatever table you're looking for. And basically, it just gives you an output with all the indexes that we've ever applied to the attendance shift locations table. And one particular way you can be able to figure out which ones are individual indexes and which one are composite indexes are basically look for those that are repeated twice or multiple times, basically. So in this case, we can see the attendance shift locations action unique index being repeated more than once, while the others are just once. And you can also see the column names to see what particular indexes are wrapping around which particular column names within the table. So in this case, you can see the the action unique index wrapping around both the attendance shift ID and the shift action column as well. Meanwhile, the individual index on shift action is wrapping only around the shift action. And another thing you need to also keep in mind is that the sequencing in index, like I said, the ordering of columns within the composite indexes are also very important. So the attendance shift ID comes first in this composite index, while the shift action comes second in this particular shift index. So for example, if I decided to run this particular query, give me all shift locations where the shift action is equal to clock in, what particular index do you think the SQL will choose in this particular case? In this particular case, you can see that we are querying the column, the shift action. Normally, what you can check now is check for the indexes that are wrapping around the shift action. And in this case, there are two indexes. Do you think SQL will be able to take both the action unique and the unaction indexes within the possible keys as indexes that can be used? In this case, unfortunately not, because we are not following the rules of composite indexes. Because like I said, in composite indexes, we need to first of all query according to how we are applying them within the indexes. So if you want to be able to use these composite indexes, we need to be able to query first the attendance shift ID, then the shift action, basically. So in this case, since we're only querying the shift action, only the individual index will be used. However, if you want to be able to get SQL to be able to get the composite index within the possible keys column, we need to be able to do queries like this. Give me all shift locations where attendance shift ID is equals to 1, 2, 3, or give me all shift locations where attendance shift ID is equals to 1, 2, 3, and shift action is equals to clock in or clock out, wherever the case might be. And the possible keys will actually be both of them in this particular case. So now that we understand a little bit, because this is just touching the surface of indexes, this is a bit broader than that, let's go back to the query. So now that we understand what possible keys are, possible keys is just SQL's way of saying, these are the indexes I think I can use for this query. And if we go a bit down, we can see the column key, where SQL is saying, okay, I'm eventually going to use these particular indexes, which are the on out of radius and on workplace missing information. And if you go to the indexes on shift location, we can see them as individual indexes that are wrapping around the out of radius and the workplace missing information. And this makes sense because we are actually querying the out of radius here, and we're actually querying the workplace missing information here. Okay, now that we're able to talk about the indexes that were used within the attendance shift locations, let us check the attendance shifts. And here we can see the possible key is telling us it is only using the primary key, and eventually it is using the primary key. This would make sense if the attendance shift did not have any indexes applied to it. However, it wouldn't make sense because, like I said, attendance shift has millions of records within it, and not applying indexes will be foolish in a way. So let's investigate. Do we have indexes within the attendance shift? So if we go to the attendance shift, do the same query as well, we can see this plethora of indexes that we have within the index attendance shift. And it's only choosing to use the primary, which is only wrapped around the column name, or rather, it's always wrapped around the ID name. So let's go back to the query. Why exactly is not using any of the indexes apart from the primary key? If we check for the attendance shifts here, we can see the ID being used. So it makes sense that the primary index is highlighted within the possible keys. However, if we check a bit further again, we can see the reference date also being used here. So probably the answer is that we do not have an index wrapping around the reference dates. So let's investigate further. So if we go to the indexes within shifts and we check the column name for reference dates, hey, we can see reference dates here and here as well. So what's the problem? For those who can, I'm sure you already get into the root of the problem. We can see inside the sequencing index that it is either the second in one of the indexes, or if we check the other ones as well, it's either the third one and third in sequence within the index, or it is the second one. So it's located within 3 indexes, but it's never the first one on the list. It's either the second or the third. So what do you think the problem is here? Somehow we are not respecting the rules of indexes, and that's why it is not even showing at all within, or SQL is not even choosing it as a possible index to be used within this particular query. And that's the very first issue that we realized. Another one that we also realized is that we're using primary, so somehow we're doing a full table scan on millions of records, which is terribly inefficient. Okay, so that explains the explain keyword within SQL. So let's go into the explain analyze and try and figure out more about the costs and what's going on there. Like I said, the explain analyze actually runs the query. So in this case, it runs like a very convoluted tree-like structure. It's a bit hard to explain, but I'll try my best to break it down a bit. And at the same time, it also gives us the actual running cost of this query. So in this case, it's like I know in my topic, I said 8 seconds. This is actually longer because I ran it after Datadog has run it, and it was actually taking a bit longer. Sometimes it actually took 10 seconds, which is way too long. But yeah, so what the explain analyze does basically is that it takes it, the way we read explain analyze is we read it from bottom to top, the more indexed to the least indexed, basically. So I'll just be going to the bottom to top, and I'll be focusing more on the actual run cost. This is the estimated run cost, so I'll just be focusing more on the other parts. And basically, from what we can see, in the first place, we're doing the index lookup on attendance shift using primary key, and that's where we are doing the join here on the attendance shift. And somehow the time isn't that bad, to be honest. The loop is actually giving us off a bit. It's looping over 390 times, which is a bit much, but it's still in milliseconds, the actual time, so it's not too bad at the moment. But if we continue to go a bit up, where we are filtering by the reference dates and also checking, this is the join, this is covering this particular part where I explained earlier. The actual time isn't that bad as well. Loop is still 390. It's not that bad as well. So if we continue to go a bit up as well to the deep duplicates, the more indexed one, we explained a bit about this index range scan that is happening using the indexes that we got from the attendance shift locations. And if we go down to the actual time, we can see a slight increase as well from milliseconds to 474 milliseconds. However, the rows is a bit, the amount of rows being processed is a bit much. So 1.5 million rows within the database is actually being processed at this particular moment, which is way too much. It's jumping from 0.0 rows here. So if you go a bit top again, the same index scan, but on and out of radius. Also, the actual time has also slightly increased to 533 milliseconds, and it's processing 1.7 million rows. And if we continue going up, we can see also that it has exponentially gone up as well to 9.25 seconds, and it's processing 3.3 million rows plus. So in a way, this is trying to tell us that even though we are applying indexes here, even though indexes are known for its fast lookups, the amount of rows that we're processing is way too much for it to be effective in a way. So if we continue going as well here, we go to the actual time, 9.45 seconds, and it is processing 390 rows, which means that somehow we are taking a lot of time just to return 390 rows in this particular part. Same here as well, 9.45, and it is reduced from the filtering to 5 rows, and finally at the end we are getting 9.4 seconds only to return 1 row to us, which is totally inefficient. We cannot be spending 9-point-something seconds just to only return 1 row to us. So what does this tell us? In a way, we are, number one, we are not respecting the rules of composite indexes, and number two, we are scanning way too many rows, even though we are applying indexes on the shift locations table. So how were we able to fix this, or rather, how did our team were able to fix this, basically? one of the things that we could do is we could create an individual index that could wrap around the reference date, but that would not be necessary since we already have 3 places where the reference date is being applied within these indexes. Another way we can also check is check where exactly or what particular column comes before the reference date. And most of it seems to be the employee ID. The employee ID comes first here. If we check the other places where the reference date is also applied within the index, the company ID comes first, then the employee ID, then the reference date. And finally, in the last index, the employee ID comes first. So in this particular case, why create a particular index when we already have the employee ID already applied here? So our fix was technically really simple. In a way, we decided to kill 2 birds with 1 stone in some ways. Number one, try to filter down the amount of data that we're going through so that it doesn't have to scan millions of records, and at the same time, apply indexes within the attendance shift for a faster lookup. So what we did basically in this case was to apply or respect the rules of the composite index here. One sec. So if I apply the attendance shift here, dot employee ID equals to this, and apply the AND here. This was technically what we did. So let's try and see how it works within the explain here. If I go to the optimize query and see what we did, this is technically what we did. We added the employee ID first, and then queried the reference date second to respect the rules. So what do we see? We see a major difference immediately. In the attendance shift locations is technically kind of the same thing as well. However, in the attendance shift, rather than using the primary keyword, the primary index only, we see those other indexes that SQL did not choose previously and is now choosing to show in the possible keys here. And then if we go to the key as well, we can see that the SQL optimizer decided to use the composite keyword for the attendance shift locations that I will explain in a bit. And rather than using the primary in this case, it has decided to use one of the composite keywords with the composite indexes within the attendance shift table. So I'm sure you're wondering why exactly the SQL optimizer decided to use this instead. In the previous one, in the optimized query, it was there, but it's really up to the SQL optimizer to be able to choose what particular indexes will be the best use case for whatever query is happening. So I'm guessing that, or rather from what I understand in my own opinion, is that the SQL optimizer knew the amount of tables it needed to filter through and decided that using 2 indexes might apply the faster lookup rather than using just 1 index in this particular case. So in this case, since we're already filtering out the shifts that's of a particular employee ID, and we're already applying an index within the attendance shift table, it decided to use the composite index that it did not use in the previous query. And if we check the explain analyze for this particular query, the same convoluted tree, which has already reduced significantly, and then from 9.455, it has significantly reduced to 0.03, a 99.9% reduction, basically. So you can imagine how mind-blown I was with this. We can also check out the costs as well. The loops have significantly reduced. The costs are in milliseconds for each particular row as well. And it was really mind-blowing to be able to understand what was going on under the hood and then being able to apply this particular change. So what are our learnings? Basically, we understood that there are over 1 million shifts that we did not filter at all, and we're joining it to the attendance shift locations, which we're filtering by the employee ID. But even though that we are even doing the indexing on the attendance shift locations in the first place, just pruning the amount of data that we needed over in the attendance shifts, and the attendance shift table, encourage us to actually use the index to encourage faster lookup, basically. So this was the one-line change that we decided to just do, just a one-liner. We added this, basically filter by employer ID, filter the attendance shift by the employer ID, and this was the scope that we added to our application record for, our shift application record, where we joined the shifts and we're able to filter by the employee ID as well. So as a wrap-up, basically, I'm just going to borrow from, I think Rosa did a really good job about breaking it down at the end, trying to understand what's going on at the background, basically. Like, I know real synthetic sugar is amazing for productivity, but then just applying all these nice syntactic sugars to your code and everything without understanding what's going on underneath, beyond the hood, basically, and getting your hands dirty, you might never know how much it would actually encourage you to prune down the issues or inefficiencies that you have within your code. And you might never know, you might be able to reduce most of your queries by 99.9% as well. Okay, thank you so much for listening again, and thank you so much for inviting me.